Hello, welcome to Intro to Statistics. In this video, we'll be discussing mean and median, interquartile range, and the standard deviation. The mean, or as it's often called, the average. Given a set of values, the mean, or average, is what each value would be if the sum of the values were equally distributed amongst them. So given a set of numbers 10, 14, 21, find the mean. You can see that these numbers are not equally distributed. The 21 has more, while the 10 has less than its share. So what I would like to do is take some from the large value, kind of playing Robin Hood, and give to the poor value, the lesser value. So I'm taking 5 from the 21, knocking it down to 16, and I'm redistributing those 5 points to the 10. So the 10 now becomes a 15. Now in essence we have 15, 14, 16. The numbers are closer together. But again, the 16 is still a little bit larger than the 14. So I'm going to take 1 away from the 16 and redistribute that to the 14. Now, our set of numbers 10, 14, 21, when we take away from the 21 and redistribute so that everything's equally proportioned, we have 3 numbers all the same. They're each 15. So therefore the mean of 10, 14, and 21 is 15. Now that's not how most people find the mean. Most people find the mean, which is written, by the way, as x bar. They find the mean by adding up the values and dividing by the number of values. So in this case, if we add 10, 14, and 21, we get 45. We divide by 3, the number of values, and we get 15. Division naturally equally distributes the values. So again, the mean or the average of our set of numbers is 15. The median. The median of a set of values is the value that separates the upper half of the values from the lower half when the values are arranged in ascending or descending order. So let's take a look at this example. Given the 5 data, 21, 25, 12, 28, 25, find the median. First, I arrange the data. I'm going low to high. 12, 21, 25, 25, 28. 25 is the middle number. It's 3 from the left end and it's 3 from the right end. Therefore, the median is 25. Think of the median like the median in the road. It's the middle part. Given the numbers 10, 14, 20, 21, find the median. In this case, they're an even number of data. So what I'm going to do is take the 2 closest to the center, they're already arranged low to high, and average those. So I'm averaging the 14 and the 20 to get 17. So we consider 17 in this case the middle number, even though it's not really a member of the data. The lower quartile is the median of the lower half of the data values. It's the middle number between the smallest value and the median. Now, when there are an odd set of numbers, as in this case, in this example, 2, 7, 10, 12, 16, 18, 23, 12 is my median. It's the middle number. It's 4 from the left end and it's 4 from the right end. Ignore the median when there's an odd set of data. Now, the lower half now has 3 data points. The middle of that, the median of 2, 7, and 10, is 7. Hence, the lower quartile, Q1, is 7. The upper quartile, similar to the lower quartile, is the median of the upper half of the data values. It's the middle number between the median and the largest value. So using the same set as above, again, 12 is the median, so I'm going to ignore that. Now my upper half of my data consists of 16, 18, 23, which are 3 values. Finding the median of that, I get 18. So the upper quartile, Q sub 3, is 18. In the set 2, 7, 10, 12, 16, 17, 23, 26, we have 1, 2, 3, 4, 5, 6, 7, 8 data. The median would be halfway between these blue numbers, the 12 and the 16, so the median would be 14. But ignore that and now look at the lower half. The lower half now has 4 data values. And again, because that's an even set of numbers, I'm going to take the median of that, which would be halfway between the 7 and the 10, and if I average 7 and 10, the 2 red numbers, I get Q1 to equal 8.5. Something else that I should point out while I'm here. The interquartile range is the difference between q sub 3 and q sub 1. 18 minus 7 is 11. That's my interquartile range. Don't expect the difference between the median and q sub 1 to be the same difference as between q sub 3 and the median. For instance here, 12 the median and 7 q sub 1 is 5. But here q sub 3 is 18 and the median is still 12, and that difference is 6. So the median's not always placed right smack dab in the middle between q sub 1 and q sub 3. So if they gave us q sub 1 and q sub 3, that doesn't mean we could necessarily identify what the median would be. Finally, we come to standard deviation. It's the measure of how much spread there is in the data from the mean, or the amount of dispersion there is in the data. The formula for standard deviation, and this is lowercase sigma, a Greek letter, is equal to the square root of the sum of the difference between each data point and the average. This is the population average, mu, where we square each of those differences and add them up, and then divide by n, and n is the number of data in our set. Let's take a look at a specific example, and I think it'll be a lot more clear. Find the standard deviation for the data set 7, 10, 16. Well, first, we'd have to calculate the population average. I would add 7, 10, and 16 and divide by 3, and we get 11. So mu is 11. N is 3 because we have 3 data values. Also, x sub 1 is our first data point, that's 7. X sub 2 is 10, and x sub 3 is 16. When I plug into our formula from above, I'm replacing sigma with these 3 terms added together. I get the square root of the quantity, 7 minus 11 squared, that's x sub 1 minus mu squared, plus 10 minus 11 quantity squared, that's x sub 2 minus mu squared, plus 16 minus 11 quantity squared, that's x sub 3 minus mu squared, divided by 3. Well, when I calculate the numerator, I get 42. So I've got the square root of 42 divided by 3, which is the square root of 14. And that's my standard deviation. It's a numerical rating of the amount of spread. To try to help bring that standard deviation concept into focus, let's consider 2 targets. So anything in the brown region scores 5 points. This person A took 4 shots. 1 landed outside the target, so that scores nothing. 2 landed in the brown, so those are each worth 5, so that's a total of 10 points. And anything in the pink region, the center region, is worth 10 points. There's another 10. So this person scored 20. Person B had all 4 shots land inside the brown region, each one being worth 5. So person B also scored 20. However, even though they have the same score, this person has a higher standard deviation because these points are more spread out. This cluster is tighter. It's a tighter shot group. It'd be easier to coach B to be a better shooter because you can see consistently B shot to the right of the bullseye. So all we'd have to do is instruct B to aim a little further to the left, and B would be very consistent, a low standard deviation. Where A, it's going to be harder to advise A because A is kind of all over the place. So A has a bigger issue, a higher standard deviation. The points are more spread out from the center. Let's pretend we had 3 test scores for 3 different classes. In the first class, our test scores were 95, 85, 75. The median would be 85, it's the middle number. The average X bar is also 85, but the standard deviation is 8.2 when you compute it. Class 2, 86, 85, 84, you can tell this class is more consistent. These were more spread out. The 95 did very well, the 75 not quite so well. Over here, everyone's pretty close to an 85. The median's still an 85, the average is still an 85, but the standard deviation has dropped to 0.8. Meanwhile, in this third class, each student scored an 85. So there really wasn't one student that scored better than any other student. The high score, the low score, the median score, the average, they're all 85. And the standard deviation in that case is 0. There's no spread in the data here. There's a little spread in the data here, and there's a much greater spread in the data here. Still further to help bring this concept of standard deviation into focus, let's consider two different cities, Buffalo, New York, and Honolulu, Hawaii. Given the data below, which city would have the higher standard deviation? Here are the average high temperatures in degrees Fahrenheit throughout the year, broken down by month, from January through December. You can see Buffalo starts at 31, works its way up to 79, comes back down to 35. The average of these numbers is 54.9. Honolulu starts at 81, works its way up to 88, comes back down to 82. The average of these numbers, 84.5. Looking at the graph of Buffalo, you can see it starts very low, climbs up a lot, and then drops a lot. Honolulu, very consistent because of its proximity to the equator. So Buffalo has a greater spread, so Buffalo should have a higher standard deviation. Honolulu, the numbers aren't spread much at all, so it should have a very low standard deviation. As a matter of fact, here are the standard deviations when computed. Buffalo's is about 17.2. Honolulu's is only about 2.6. Buffalo has a much higher standard deviation, a much greater range or spread in its data points. Which would have a higher standard deviation, the weights of humans or the weights of vehicles? Well, let's think about that for a moment. Here are 5 randomly selected people and their corresponding weights. The person on the left is 195 pounds, the person in the green shirt 185, the middle person 220 pounds, the person with the vest is 170 pounds, and the person in the striped shirt 190 pounds. If we calculate the average, we get 192 pounds. That's adding up all their weights and dividing by 5. Their standard deviation is 16.3 pounds. That's a decent amount of spread. But 16.3, let's look at vehicles. A Ford Escape is about 3,500 pounds. A Ford F-150 is about 5,100 pounds. A Chevy Corvette is about 3,600 pounds. A Dodge Dart is about 3,148 pounds. A Camaro is about 3,700 pounds. A Jeep Grand Cherokee is about 4,900 pounds. And a big rig, a semi-truck, is about 1,900 pounds. You can see these numbers have a lot bigger spread than people. We range from, in this case, 3,148 all the way up to 19,000 pounds. The average is 6,145 pounds, but the standard deviation is 5,293 pounds, much larger than the 16.3 that we had when we considered the people. Generally speaking, when you have larger numbers, there's probably going to be a greater spread in your data than when you have small numbers. If we're measuring the weights of ants, there's not going to be much variation between the weights of ants because from the heaviest ant down to the lightest ant, there's not going to be a great difference between them. So they would have a low standard deviation. Now, how do we use our calculator to get statistics on a frequency table? Let's say we have 2 companies, each with people grouped similarly. The lowest 8 employees are all paid equal amounts, except in this case, the lowest 8 are only paid $30,000 at company A, where they're paid $48,000 each in company B. The next 9 people all have the same salary, $40,000, where in company B, the next 9 people are all paid $51,000. In company A, 5 are paid $50,000, 2 are paid $75,000, 1's paid $280,000. That's the top dog. Over here, 5 are paid $53,000, 2 are paid $55,000, one's paid $62,000. The average in both cases is $51,200. The median in both cases is found in the second group. Why? There are 8 values that are above this group, and there are 8 values below this group. So the median would occur in the center of this group, which is going to be 40,000. Likewise over here, 8 below and 8 above this group. So the median is going to occur in this, and that's going to be 51,000. So the median over here is much higher than the median is over here, even though the averages are the same. But look at the standard deviations in salaries. $48,255 compared to $3,124. These salaries are much closer together. These salaries are much further spread out. But how can I get these numbers from my calculator? Well, go to Stat, select Edit. Now I preloaded L sub 1 and L sub 2 lists with the salaries and the frequencies. Hit Stat again. This time go to Calc, one variable stats, L1, L2 is our frequency list, and then hit Calculate. What you'll see, X bar 51,200, standard deviation sigma 48,255. There's a min, Q1, median, Q sub 3, and the max, 280,000. Now, if I want to get data from the second group, since the frequency list was the same, I just need to put in the new salaries for salary groups. 48,000 was the lowest group, and 62,000 was the highest end. Now we can go back to Stat, again calculate, one variable stats. This time my list is in L3, my frequency list is still in L2, and then hit Calculate. Again, I can see X bar is still 51,200, but now my standard deviation is about 3,124. And the rest of the stats are still given. The median, 51,000, and the max, 62,000. So again, you can see that this just confirms what we got when we were using our calculator. If we don't have a frequency list, so we didn't have 8 sets of 30,000, 9 sets of 40,000, etc., and we just put in this, make sure when you use your calculator and you go calculate one variable statistics that you clear out the frequency list. In our next video, we'll be discussing the normal curve with standard deviation, because a lot of data falls along this curve, where here is our average, and most data falls within one standard deviation of the average. So we calculate the standard deviation, and most of our data, about 68%, fall within one standard deviation, either to the right or to the left, either above or below. So say we're talking about heights of people. Most people are close to the average height. But every once in a while you get an outlier way out here who's extremely tall. I mean, really tall, like over 7 feet tall. Something that's away from the norm, something abnormally tall. So again, norm is what's accepted or kind of customary, usual. Ab is away, so abnormal is way out here. Abnormally short would be over here. All right, that's my video on statistics, part 1. I'm Murray Wright. Thanks for watching.